here, really what we're talking about is electromagnetic waves inside conductors. Okay, so so what do we have here? What we did in the past with conductors was really treat things that were static, that were time independent. We viewed conductors as setting boundary conditions for our Laplace equation, giving us, according to Green's theorem, all the information we needed to compute the potential throughout space. Here we are doing electrodynamics. So things are moving around. And therefore, there can exist electric fields inside conductors. It's just that they disappear very fast. But they can be there and they have an effect. And the effect that they would have would be understood by saying that actually in our conductors, we've got some charges moving around. And here we've got some, say, free charge density somewhere inside our conductor that would be characterized by being along the applied electric field and of a strength which is characteristic of the actual conductor that we are talking about. So there's a proportionality coefficient here, which is the conductivity. And this is really nothing but a kind of microscopic description of Ohm's law. Okay? Of course, when I apply an electric field, the conductor is going to react to this. Charge is going to start flowing, and charge flowing is going to correct the charge densities in order to cancel whatever electrical field I've put in there. But while I've put the field, the instant I've put the field, there is charge moving. Okay, and it's characterized by this. So this is a kind of assumption that that we make that is, pretty damn precise. So let's just again go back to Maxwell and see what Maxwell tells us in those circumstances. Well, so what did we have? So we still have Gauss's law. Div E is rho F. And now we're doing things in matter. We're assuming a linear isotropic conductor. So linear isotropic. Namely, we do Maxwell in matter, and we assume that the direction doesn't matter, and the intensity of whatever we have is proportional to, so the polarization is proportional to the electric field. Magnetization is proportional to B or to H, said otherwise. So we can just use straight Maxwell's equations in matter. So then here I put just the epsilon characterizing this. So this is the permittivity of that field, of that medium. And then so I have also my Faraday's law minus dB dt. I still have that my div of B is equal to 0. And if I look at Ampere Maxwell, then now here I would have mu 0 or mu J free. But now here I'm going to replace J free straight with the conductivity times the electric field. So this term here immediately becomes, instead of mu 0, mu JF, it's mu sigma E. Okay, and then I still have the in matter equivalent of the Maxwell term, so the displacement current, dE dt. Okay, so these are my Maxwell equations. Now, essentially, first thing to note. We've got the continuity equation for the free charge, d rho f dt plus div of jf is equal to 0. Okay, so we had seen that we can prove the continuity equation directly from the Maxwell equations. Conservation of charge, therefore the continuity equation and for the free charge itself. Now, if we put directly Ohm's law into this, what this tells us is that the time derivative of the free charge density with respect to time is, you see, I've got, I put this on the other side. Now I've just got minus sigma times div E, minus sigma times div of E. But div of E by Gauss's law is just proportional to the free charge density divided by the permittivity. So here I've got some coefficient sigma over permittivity with rho f. Okay. And the solution is that my rho f as a function of time, so if I have a certain r here and I have a certain time, it is a decaying exponential in time, starting from some initial value. So rho free at some position r time t is the density at some position r 0, e to the minus some characteristic time scale. So let me write it as, well, you know, I could write it straight as sigma over epsilon t, like this. Okay. It decays exponentially in my conductor, which kind of makes sense, right? So, so here I can rewrite this as e to the minus t over tau, where tau is just epsilon over sigma, and this thing in metals. This is like something like 10 to the minus 18 seconds. Okay, so an attosecond. This is absolutely stupidly fast because, of course, there's a lot of charge available in a conductor that is very mobile. So whatever you have is going to be compensated for extremely quickly. So in practice, essentially, a time scale of a femtosecond, so 10 to the minus 15 second for a metal, is like moving slowly. Okay, so so what that means here is that really in our metal, despite the fact that we've got time-dependent electric fields creating currents through Ohm's law, these currents cancel any free charge that has developed anywhere on a time scale which is way too fast for being of any interest to the propagation of electromagnetic waves in these media. Okay? So what that means really is that we can say, well, okay, going back to the Maxwell equations, whatever free charge that we have in there is going to dissipate on a time scale which is way too fast to affect anything that we're doing. So we can just put this free charge to 0. Kind of say we just like wait a tiny bit and this thing just decays exponentially everywhere. So the right-hand side of Gauss's law here is just 0. Okay, it just completely dissipates. So therefore, the effective Maxwell equations. So after the free charge decays, which is very fast. Then what we get is just a simpler set of equations. Div E is equal to 0, div B is equal to 0, Faraday, and then Ampere Maxwell, which just tells us mu sigma E in this case, plus mu epsilon dE dt. Okay, so these are the equations that effectively describe the propagation of an or the electromagnetic fields inside a conductor when things bounce around very, very quickly. Right? So the point is that the same logic as before applies. To get a wave equation. So I remind you what we did. What we did is we took the curl of the fourth equation. Or actually, maybe we can just do it with this one here. Okay, so that's a thing. And the point is that this thing here, by an identity, is the gradient of the div of E minus the Laplacian of E. Okay, and this one here, I can just use Ampère-Maxwell. Yeah, which is this equation here, in order to obtain a wave equation that now looks dangerously similar to what we had before. So I've got the Laplacian of E, and I've got now the second time derivative of the E here, so mu epsilon second time derivative of E. But now there's an extra term. There's this term here. Okay, so I've got plus mu sigma dE dt. Okay, so that's the extra term. It looks like a kind of friction term that we have in there, and you'll see, yeah, you'll see kind of why. So a free wave solution or a free wave ansatz for a solution. Now we're trying to solve this equation here. And you see, if I only had these two terms, I would still like to have some e to the I k dot r minus omega t, and then that would work. So I'm still going to use something like this. I'm going to use E of RT is equal to some initial amplitude E0 with e to the I, and now we'll gloriously call it k twiddle dot r minus omega t. If I substitute this ansatz in this equation here, you see I take two spatial derivatives, I take two time derivatives, but then I take one time derivative here. So there's something funny going on here, because in order to solve the wave equation, this is the wave equation. To solve the wave equation, you need that this k twiddle squared is equal to some complex number. Mu sigma and then 1 omega. Okay. So this k is now complex. Okay. And actually, so I don't have the time to do the whole derivation here. But if you do simple algebra, what you can do is you can write k twiddle as k plus I kappa, where now k and kappa are real. Okay. And k is equal to, let me write it, k plus, and kappa is equal to k minus, where k plus and minus are just some combinations of the things. So it's proportional to omega, mu. I'm just writing the answer. It's really just straightforward algebra. Actually, you need to take square root after square root to get it, but you'll square root here, plus or minus 1, and then this whole thing also in a square root. Okay, so it really is straightforward algebra to get this. Now, understand what this means. What this means is that the electromagnetic wave that we have in this conductor behaves in an attenuated way. There's a part that oscillates, as you would expect, but it also decays as it propagates. So D, by definition, 1 over the modulus of K, is known as the skin depth. Okay, so boundary of the metal here you've got your metal, you've got the electromagnetic wave coming in, and then suddenly inside the metal, so if I just imagine, I'm kind of doing the boundary like this, the electromagnetic wave, it would have an E field that would decay as I move, and it would have a magnetic field that also would like follow the same thing and decay. Okay, so the wave is attenuated as it goes in the metal, but it does go in a tiny bit. Okay, and this skin depth, you see, it's related to the conductivity of your metal. The really fun thing is that this is also frequency dependent. So I think this is essentially as complicated as you're going to get now with electromagnetic waves. You now have an electromagnetic wave that comes into such a conducting system, and the electromagnetic wave itself, first of all, decays as it penetrates in. It dies out, but it dies out on a length scale that is given by a skin depth, which is itself dependent on the frequency of the wave. Okay, so if you have something that has low conductivity, then it's going to live on for quite a while. If it has a high conductivity, it's going to die out quite quickly. If the frequency is extremely high, yeah, then you have to watch, because you see there's going to be a kind of frequency dependence in all of this. So you can see different frequency waves going more or less deep inside your metal here. But you see, the whole physics of this requires mathematics, which uses in principle nothing more than everything we've done. It's just that in this case, there's a bit of complex analysis that goes into that, but really algebraically, it's the same kind of thing. Question?
Yeah, is the skin that one of the kappa? Okay.
So kappa. This is kappa. So the kappa. I'm sorry?
Kappa is minus K.
Yeah, so this is just a notation that I have. So just to be able to define them both in a thing. So there's a parameter called K plus or minus, where you've got this different sign here. And essentially, so the K, so the oscillatory part of the wave is given by the plus here, and the decaying part of the wave is given by the minus. So for example, you see if you go to some very high frequency here, then you need to expand this this square root, get a 1 over square, but then you've got a -1 here. So then the omega dependence essentially stops showing up in this when omega is very much larger than sigma. But then the sigma itself also, it gets complicated, because the sigma itself, due to the physics of your conductor, also should have an omega dependence. So there's a whole storyline now developing about the propagation of electromagnetic waves in imperfect conductors in different geometries. And this whole branch of physics is now completely accessible to you because it makes use of these equations and essentially nothing else. Okay, so so that's just to kind of open up the door for those of you that might consider these things. So for example, also even in astrophysical circumstances, you can also think of propagation of your light as propagation in these imperfect media that have frequency dependent response, and you could treat those problems with those equations here. Okay, so I think I'm over time here. My apologies. Next time I will actually take a little half hour to do waveguides, which was meant to be done today. I didn't manage, but I'll do that then at the beginning of next time with, you know, my sincere apologies for the delay.